Alright, in this video we study some of the basic properties of the Riemann integral, and as you will see, most of these properties are derived from the fact that the Riemann integral is a sum, essentially a sum of small regions. So hopefully most of them are not so hard to understand and easily make sense. Okay, let's start. Okay, first property is this. Suppose we have a less than b less than c, and if we integrate a function, of course we assume this function is integrable, or Riemann integrable, integrate from a to b and add it to another integral from b to c. This is equal to the integral from a to c of the same function. Okay, what does this mean? So as we have seen, the integral is basically the area enclosed by the function and the x-axis, right? So this area. So this is a, this is c, and somewhere in between there is b. Okay, so the right hand side, this means the area, this whole area. And the first integral on the left hand side is this area, so between a and b. Okay, so if we add this area to another area between b and c, this area, then we get the entire area. So that's what this equation means. And related to this, we adopt the following convention. So usually if we integrate from a to b of some function, we assume that this lower bound is of course less than the upper bound. That means a is less than b. But we can actually define the opposite case. So integrate from b to a, where a is less than b of f of x dx. And this is interpreted as negative of a integral from a to b and f of x dx. Okay, so this is the usual integral where this a is less than this b. So lower bound should be, of course, less than the upper bound. But we can swap the upper bound and lower bound by putting the negative sign. So instead of, it's like instead of integrating from here to here, we integrate from here to here, but we negate the sign by putting this negative sign here. And if we adopt this convention, then this equality holds irrespective of the order of these three numbers a, b, c. So whichever is bigger or smaller, we still have the same equality. So whenever we have this lower number greater than the upper number, we can just swap and negate the integral, and we still get the same result. The next property is the linearity of integral. Okay, so suppose we have two integrable functions. Integrable on a closed interval between a and b. Then let's say k and l are some constants, real numbers. Okay, then the integral of a linear combination of these functions, integrable functions, is, guess what? It's a linear combination of integrals. Right? So this is a linear combination of a function, of two functions, and we integrate it. The result is the linear combination of the integrals of each integral of each function. Right. And as we said before, since integrals are just a limit of summations, right? So this property is actually inherited from the linearity of sums. So something like this. Sum of a linear combination of two sequences is the linear combination of the sum. sums and L and IBI. So this property is inherited to integrals. The next theorem is one of the most fundamental results of the Riemann integral. That is, any continuous function on a closed interval is Riemann integrable on that closed interval. So let's write it down. A function that is continuous on a closed interval between a and b is integrable. So of course Riemann integrable on the same closed interval. So I don't give the proof for this theorem in this video, but hopefully I will give it the proof in another video. So for the moment, for a while, you can use this theorem almost like an axiom of Riemann integral theory. And the next theorem is actually called the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus. And it says the following. Next, we introduce the Fundamental Theorem of Calculus. The fundamental. So this sounds very important, and it is. Mental Theorem of Calculus. Okay, so that says the following. So suppose we have a function f of x that is continuous on an open interval. It's not closed interval, open interval I. And let a be a constant in this interval. So it's a constant. And x be some value in this interval. Okay, so these two values are within this open interval, and then f of x is, according to the previous theorem, all continuous function that is continuous function on a closed interval is integrable, right? So f of x is, maybe I shouldn't use x here. Let's use t instead. So f of t is integrable on either a to x or x to a, right? So if x is greater than a, we use this interval, and if x is less than a, we use this interval. So this is integrable because it's a continuous function on a closed interval. That closed intervals are this or this. And then let's define a new function, f of x, by an integral of f of t from a to x. Okay, then this is the result of this theorem. Then this function, new function, capital F of x, is differentiable. And the derivative is f of x. So this f is this f, right? So this is called the Fundamental Theorem of Calculus. This theorem is important because it gives us a way to actually calculate an integral, right? So if we can find such a function as this capital F of x, then that is the integral of the function, right? So if we have some function, lowercase f of x, and if we can find some function such that its derivative is our given function, then the integral of this lowercase of f of x is this uppercase f of x. Okay, so calculating the integral of a function becomes a matter of finding some function like this. Okay, so let's prove this theorem. And it suffices to show the following, right? Because we want to show this. What this means is, according to the definition of a derivative, what we need to show is this. Limit h goes to 0, capital F x plus h minus capital F of x over h is equal to lowercase f of x. So if we can show this, so this limit becomes lowercase f of x, then we are done. Okay, so let's do that. First, let's consider this numerator. So we define this capital F as in terms of this integral, right? So this is, according to the definition, is equal to integral from a to x plus h of f of t dt minus integral from a to x and f of t and dt. And using the property of integrals, this is equal to, let's see, so we are, okay, let's draw some picture here. Suppose we are integrating from a to x and a to x h. So function is something like this. And we first calculate this part and subtract from that this part, right? So the result is this part. Okay, so that means this difference of integrals becomes the integral from x to x plus h, f of t, and dt, right? And now, let us define the following. Lowercase m is equal to minimum of this function value in this interval. Okay, so I should write x. T is between x and x plus h, and uppercase m is the maximum. And t is between x and x plus h. And also we define capital S and S in the interval. Such that f of lowercase s is equal to the minimum and f of uppercase s is equal to the maximum. So, finding the minimum and maximum, it's possible because we're assuming that this function is continuous in this interval, right? So according to the extreme value theorem, this is possible. So extreme value theorem. Okay. Now, because of the way we define m, this lowercase m and uppercase m, that means, so lowercase is the minimum. So if we calculate this area, that, the area of this smaller rectangle is less than the area of this integral, right? So m, lowercase m times h is the width of this interval, is less than or equal to the integral of the function between x and x plus h. And by the similar argument, this integral is less than capital M times h, because capital M means the maximum of the functional value or in this interval. So that corresponds to this bigger rectangle that covers the entire area under the curve. So we have this inequality. So that means if we divide everything by h, we have m greater than x integral of t dt over h and m, right? And this m is equal to f of lowercase m, and this uppercase m is equal to f of uppercase s. So as h goes to 0, then lowercase s goes to x, and uppercase s converges to x. So both converges to x. So that means since the function lowercase f is continuous, this converges to f of x, and f of uppercase s also converges to f of x. So by the squeeze theorem, so this converges to f of x, this converges to f of x. That means the middle, this one, also converges to f of x. So this converges to f of x. And we are done. Okay, that's all for this video. See you later.